Okay, today we are going to move on with the push-down automata. Okay, so we can start with the push-down automata. So here, for regular languages, we have seen finite automata, isn't it? So for the context-free grammar, for context-free languages, we'll be dealing with the push-down automata. So for context-free language, the acceptor is the push-down automata and the generator is the context-free grammar. Okay, so this push-down automata accepts context-free languages. Okay, so here in the finite automata, we'll be having that is only the current state is known. So for the automata, only the current state is known. Here we'll be using a star to keep track of the information. Okay, so infinite amount of information can be okay. So here we'll be using a stack. So using the stack, we can store infinite amount of information. Right. So here, if we are using a stack, we can only access the topmost element. Top the stack element can only be accessed. So here, please make a note. In the case of finite automata, only the current state will be known to the machine. So in the push-down automata, we'll be going for a data structure that is a stack. So in this stack, we can store infinite amount of information. So while accessing the information, only the topmost element of the stack can be accessed. That are you all aware of, right? So in the stack, we can access only the topmost element. So this is your finite state machine. Okay. So finite state machine, that is the finite control. So where will be giving the input to the finite control. So here this finite control will be making use of the stack. It will be making use of the stack, and then it will say whether it is accepted or rejected, whether the given language is accepted or rejected. So it is a combination of finite automata plus stack. Okay, finite automata plus stack. So it is almost similar to the finite automata. So here, in addition to the finite automata, we will be making use of this stack as well. We will be making use of the stack to perform the checking of the particular pattern. Okay, so here we have to deal with the formal definition of push-down automata. So here the formal definition involves 7 tuples. Formal definition of final push-down automata involves 7 tuples. Right. So here first the 7 tuples are represented by Q, sigma, tau, that is the stack alphabet. Okay, then delta, that is the transition function. Q naught, the start state. Z naught, the start symbol of the stack. And F, the final set of final states. Please make a note over here. So here Q, sigma, delta, Q naught, F were already known to us. So that is we have discussed in the finite automata. Right. So Q is nothing but a set of finite set of states. Sigma is the final set of input symbols. The delta is the transition function, and Q naught start symbol, and F is the set of final states that we are all aware of, already aware of. So two new tuples we are coming across is tau and z naught. Here we are making use of stack, right? Inside the stack, we'll be pushing some elements. We'll be dealing with this stack. We'll be pushing and popping out some elements, isn't it? So those elements are called as the stack elements. It is not mandatory that only the input elements needs to be pushed inside the stack. Instead, we can include, based upon the requirement, you can insert and push any of the element inside the stack. Okay, so so tau represent the set of stack alphabet. Okay, tau represent the set of stack alphabet. It will be clear to you when we see the example. Okay, and Z naught represents the start symbol of stack. Okay, start symbol of stack. That is, so here the bottom of the stack we have to designate, right? Bottom of the stack we have to designate. So bottom, so initially we will be having Z not inside the stack. So the Z naught will be initially placed inside the stack, which will designate the bottom of the stack. So why we are using the stack? Again, when we see the examples, it will be clear to you. Okay, just please make a note of all these 7 tuples. So only new thing we come across is these two. That is tau represents a stack alphabet and Z naught represents the start element of the stack. So here again we'll be discussing the deterministic. We can have a deterministic push-down automata and non-deterministic push-down automata. So deterministic, non-deterministic, I hope you're already aware of these terms. So here, what is deterministic finite automata? So for each input symbol, for each state, I can have a transition for only one particular state. So from a specific state for same symbol, if it is possible for me to have transition to different state, then it is called as non-deterministic, right? Non-deterministic finite automata. Similarly, the same thing with the push-down automata as well. Okay, so in the case of deterministic push-down automata, that their transition function will have state cross sigma, that is here epsilon will also be included, right? Cross. So here we'll be having stack alphabet as well. Okay, so in the previous case will be in the finite automata, we will be dealing only with the set of states and the input alphabets. So here we'll be dealing with the stack alphabets. For that, I'll be having transition to Q cross tau. Okay, and then so just make a note of it. That's it. Okay, Q cross. So in the case of non-deterministic, I'll be having this many number of transitions. Sorry. Okay, so from each state for the same input symbol, for stack symbol, I can have transition to multiple states. That is non-deterministic. Okay, so in general only we are going to discuss with that of the push-down automata. So just make a note what is non-deterministic and what is deterministic push-down automata. Okay, so here the case of push-down automata, it is nothing but stack combined with the finite automata. So similar to the finite automata, only thing we'll be dealing with the stack over here. So because of the stack, the formal definition of push-down automata will incorporate 2 more tuples, one is stack alphabet and the start symbol of the stack. Okay, now we can start with a small example where we are going to design a push-down automata. Before designing the push-down automata, we can see how the stack is involved in performing the operations, performing the pattern checking. Okay, A bar n, B bar n, where n is greater than or equal to 1. Here, what is the thing? A bar n, B bar n. So, can you design a finite automata to check this condition? Is it possible for us to design finite automata to check this condition? What happened now? Can we design a finite automata to check this condition?
Yes, ma'am.
Please do check this sequence. So as you say, I can check A bar n, B bar m. So here that is a sequence of A's and then comes the sequence of B's. Yes, I can check it with the finite automata. Here what happened? Equal number of A's and equal number of B's. Is it possible?
No, no, ma'am.
So here that is the constraint. So here in this case, we are checking whether number of A's and number of B's are equal. Okay. So if there are 3 A's, there should be 3 B's. So in the previous case, we can see first I should have sequence of A's and next I should have sequence of B's. Yes, very well, we can identify it. So whereas the counting, so based upon the number of symbols that comes in the front, I should have the same number of count in the next set. So that counting process, it is not possible in the finite automata because only the current state we can know. Whereas in this case of push-down automata, we'll be using a stack where we can store infinite amount of information. Okay, so how here we can start with taking a simple example, A, B, B. Yes, as you all aware, this belongs to this language, right? So 2A, 2B. How am I going to use the stack to check this particular condition? This is my stack. As discussed, the bottom of the stack will be designated by Z naught. Okay, bottom of the stack is designated by Z naught. Right. So here, this is my stack pointer, and this is my pointer to the track the input. Okay, so here this is stack pointer, and I'll be tracking the. So here, please make a note. I'll be making the functionality, that is making a transition only based upon the input symbol, as well as, so here in this case we'll be considering the input symbol as well as the stack symbol. Based upon that only we will be taking a decision, right? So here this is the input point, that is, in order to scan the input, this is the pointer, and the stack pointer is this one. So here you can see, so stack pointer is Z naught, and my input symbol is A. So what I will do is that I will push A inside the stack. Okay, I'll be pushing A inside the stack. So A is pushed inside the stack. So what happens now? Pointer will be here and here. Okay, so please make a note here. Initially, my top of the stack symbol is Z naught, and my input symbol is A. So what is the meaning? My stack is empty. So I have to push A inside the stack. Okay, so I have pushed A inside the stack. Next comes top of the stack symbol is A, and my input symbol is A. Both are same. So what I will do, I'll be pushing again A inside the stack. Okay, I'll be pushing A inside the stack. Now my stack symbol is A and my input symbol is B. What I'm doing is, so what is our target? I have to check whether number of A's and number of B's are equal. So for checking this condition, making use of this stack. Okay, so what I have to do is, if there is one B, if I'm coming across a B over here, and my top of the stack element is A. So what I will do is, I'll be popping of A from the stack. So this will be my status of stack. Okay, so here, yes. Now again, input symbol is B, top of the stack element is A. What I have to do, I have to proceed with popping operation. Oh, yes. Now input symbol is epsilon, top of the stack element is Z naught. Okay, input symbol is epsilon. So epsilon in the sense, what is the meaning? I have reached the end of the string. Okay, I have reached the end of the input string, and my stack is also empty. Okay, empty. So by this, what we can conclude? We can conclude that A's and B's are of equal in count. So we can check this with different varied terms. Okay, so here you can see. Is it not what I should do? I will push all A's inside the stack, right? So this is my top of the stack element, and this is my input symbol. So if I encounter B here and A here, what I should do? I'll be popping off. Okay. Now this here B, here A. What I should do? Pop off. Now here epsilon, here A. So what is the meaning? So it is not of equal count, right? Similarly, if the number of B's are more, I'll be having a single B here, and I will encounter Z not here. Okay, so by that, by this condition, that is, I'm encountering an epsilon and I'm encountering a Z naught. So by this, we can say that number of A's and number of B's are of equal count. So for this only, we are going to design the push down automata. Are you clear with this example?
Yes, ma'am.
Yes, just for this, so it is a very easy one, right? So just this is the logic behind. We are going to, for this, we are going to try designing the push-down automata. So in the push-down automata, we will be coming across three functionality. One is push, pop, and no operation. Okay, push, pop, and no operation. So here, yes. So what is push? So for example, if I'm having, so here this is input symbol and top of the stack symbol is B. Okay, so the first element is the input symbol, input alphabet, Here B is the stack alphabet, top of the stack element. And then if I want to push it, then I'll be representing it like this. That is, on top of B, I have to push A. Okay, A, B should be. So this is the representation for push. So please make a note. If I want to, so this is my input symbol. So this is input alphabet and this is stack alphabet. Okay, so if I want to perform push operation, then I'll be representing like this. Then what about pop? So my input symbol is A, my stack symbol is B, then pop is represented by epsilon. Okay, so here on by this, I'll be popping off the topmost element from the stack. Okay, MT represents I am popping off topmost element from the stack. Next comes no operation. Input symbol is A, topmost elements, top of the stack element is A. Okay, then I have to perform no operation. Okay, no operation. So these three are the operations we'll be using in the push down automata. Okay, just make a note. It will be clear when we see further examples. Okay, so here we can start with, as usual, similar to the finite automata, we will be having a start state, which is represented by an incoming edge which comes from over, and the final state is represented by the double circle. Okay, let me take the same example. AA, BB, the same stack. So the stack by default is will have the Z naught as the bottom end. Okay. So this is the initial condition. This is the initial configuration. So what I'll be doing? So here I'm coming across A. Okay. My stack input symbol is A. My top of the stack symbol is Z naught. What should I do? What should I do?
Push A.
Yes, push A. So what I have to do, so for all A's, I should be in the same state. Yes, yes. So A, Z naught, perform push operation. So let me be in the same state Q naught. Okay. After A's, I should have B. So only if I come across B, I'll move on to the another state. Okay. Till that point, I'll be in the same state Q naught. So yes, A is pushed inside the stack. Now this is the top of the stack element, and this is the input symbol. So A, what should I do?
Push A.
Push. So A,
A. A.
A. That's it. So now A is pushed inside the stack. Now top of the stack element, sorry, input symbol is B, top of the stack element is A. What should I do? I have to perform pop operation. Yes. After these, I should not have sequence of A's, right? I should not perform push operation. So what I will do, I will be moving on to the another state. Okay. If I encounter a B, that is my input symbol is B, my stack symbol is A, I'll be performing
Epsilon.
I'll be in state Q1. Okay, I'll be in state Q1. So now again, yes, this is popped off. This is popped off. Now my stack symbol is B, my input symbol is C. So again, what should I do? I have to perform pop operation. Whatever may be the number of A's, I should be in the same state till I encounter an input symbol as epsilon, right? So what I'm doing, E, A, epsilon, I am in the same state, right? So now my input symbol is epsilon, my top of the stack symbol is Z naught. What should I do? I have to reach the, so what is the
state?
So it is the final state, yes. So epsilon Z naught, here I can proceed with a no operation, okay? Z naught, I'll be reaching the final state Q2, right? Are you clear with this?
Yes, ma'am.
What about others, ma'am?
Yes, ma'am.
It's good. Okay, this is one form of, yes, thank you, ma'am. This is one form of representation. So here, this push-to automata can be represented. Just for this example, please make a note of it. Further, we'll be dealing with the design the push-to automata alone. Okay. So here, this is the another representation of representing the PT push-to automata. That is delta of Q naught. I am in state Q naught. My input symbol is A. My stack symbol is Z naught. Then I have to proceed with. So my transition would be to Q naught and my action is push. Okay. And then Q naught, my input symbol is A, my stack symbol is E. So I'll be having transition to Q naught. My operation is push. Next is I am in state Q naught. My input symbol is B. My stack symbol is A. I have to make the transition to Q1 and my operation is pop. This is next other way of representation. That's it. Okay. So my input symbol is Q, sorry, my state is Q1. My input symbol B, stack symbol A. I have to have the transition to Q1 and pop operation. I am in state Q1. My input symbol is epsilon. My stack symbol is Z naught. Then I have to move on to state Q2 and no operation. Okay, so this is the other way of proceeding with representation of PDA, right? Okay, that's it with this example. We can move on to another example. A per n, B per m plus n, C per m. N m greater than or equal to 1. So for the same thing, we have discussed the context breakdown, right? Now we are discussing the push-down automata. That's it. Okay. So here how we can represent this as first. So please do write the representation. So what is the meaning over here? Number of A's and number of
En,
C's are
Bn,
huh?
En,
A and
A
B
and
and
Bn,
B's, B to the power and
yes.
C n.
Good. Good. Okay. So yes, same thing. So what we have to do. So here what we will be dealing with. So what should I do first? I have to check whether the number of A's and number of B's are equal. Okay. So after checking this, if they are equal, what I'll be reaching my stack, I'll be reaching the top of the stack symbol as Z naught. Okay.
Z naught.
After that, if I'm encountering an input symbol as B, again I will be start with the pushing operation. I hope you can try on your own and then we can see this example. Okay. Just try with the stack or just try with designing the PD. Just 1 or 2 minutes. Hope you all have been trying with this. Okay, we can start now. Okay, so let us take a simple example. So directly we can start designing the push-to automata. Okay, I am in state Q naught. This is Z naught. This is the initial configuration. So my stack symbol is A. Sorry, my input symbol is A. My stack symbol is Z naught. What should I do? So first, you please do think of the logic. After it is clear for you, you can proceed with designing. Okay. Yes. So we have to.
A comma Z naught.
Yes, we have to perform the push operation. Okay. And then I can be in the same state Q naught. Okay. So A Z naught, I have to proceed with push operation. Yes, good. So now here, my input symbol is A. My stack symbol is A. What should I do? Push operation. Yes. A, A. Yes, it is pushed inside the stack. Right? Now my input symbol is B, my stack symbol is B. Right? So what should I do? First, I have to count whether number of A's and number of B's are equal. Okay? So what should I do? I have to perform pop operation. Yes. B, stack symbol A, I have to perform pop operation. I'll be in state 2. Again, here B, yes, this is popped, right? Here, A, B, A. Again, I have to proceed with pop operation. Pop operation. A, yes, good. Pop operation. Now, this will be my configuration. Okay. My input symbol is B, my stack symbol is Z naught. So, what is the meaning? I have popped off equal number. So here the A's and B's are matched. Number of A's and number of B's are matched. So only we have reached the condition of Z naught here. Okay. So now what should I do? I have to push all the B's inside that. Yes. So if I encounter a B and Z naught, I have to deal with push operation. I can be in the same state Q1 because I'm not changing the input symbols, right? So same symbol, so I can be in the same state. Yes, B is pushed in the step. Now B, B. What should I do?
Push again.
Push operation. Yes, now all B's will be pushed inside the stack. All B's are pushed inside the stack. Okay. So now we are in this state only, right? My input symbol is B. Sorry, input symbol is C. My top of the stack symbol is
B.
B. Okay, so what should I do?
Pop
I have to
operation.
go on to another state and then I have to perform pop operation. State cute. Now, whatever may be the number of CU counts, I have to perform the pop operation. C and B mapping, I have to perform the pop operation. So C, B, pop. Okay. Now I'll be reaching the state. Epsilon and Z naught. Right? My stack symbol is Z naught, my input symbol is epsilon. So what is the meaning? I have check the count of A's and B's equivalent to the number of B's. Okay, A's and C's which is equivalent to the number of B's. So stack, yeah, that is stack is also empty, my string is also over. Epsilon, Z naught, my operation, I'll be reaching my final state. Right. So it is very simple. So already we have seen the grammar, right? So similar to that one, we are dealing this one. Okay. So if you have any queries, so please do interrupt and clear your doubts. Okay, because the same thing we'll be discussing now. If it is not clear at one point, then it will be feeling difficult. That's why. Okay. A bar n, B bar n, C bar n plus n. What should I do here? How it can be rewritten as
A power N. B power M. C power N. C power n.
So first what should I do? I have to push
Yes.
A,
Okay.
push
Then
B.
you have to check B and C equal, and then
Yes,
check A and C.
good, good. Okay, all of you please do try now. Let me give you 2 minutes time. Please do try designing the problem. Okay, hope you have completed. It is a very simple one, right? Okay, we can start with, yes. Let me have a simple example. Mm. Okay, so what should you, I'll be having a stack. They not, yes, my stack symbol is A. This is the initial configuration. Input symbol is A, stack symbol is Z naught, and in state Q naught. So what should I do? I have to push A inside the stack. Okay, so A, Z naught, perform push operation. I'll be in the same state Q naught. Okay, I'll be in the same state Q naught. So A is pushed inside the stack. And then next is A, A. Okay, so top of the stack element is A. My input symbol is A. Again, what should I do? I have to perform push operation. Yes, push inside the stack. All right. My input symbol is B. My stack symbol is B. My input symbol is B. My stack symbol is A. What should I do?
We need to push.
Yes, push. It is so. Please make a note over here. So input symbol B, stack symbol A. Okay. Input symbol B, stack symbol A. So we can be in the same state. Right? We can be in the same state because we are checking this
Yes.
condition, right? So we cannot, also it is not required to move on to the further space, right? So yes, so here itself you can write. So input symbol B, stack symbol A, I have to perform push operation. Yes, B is push inside the stack. Again, so whatever maybe the number of B comes, I have to push inside the stack till I see the topmost element as B. Okay, so B push inside the stack. So now this will be my stack configuration. Okay, this is my stack configuration. Now my input symbol is C, my stack symbol is B. What should I do?
Pop.
Pop. My input symbol is B, C, my stack symbol is B. I have to perform pop operation. After that, I have to move on to the other state. Okay, so because you have to perform pop operation, I can reach this particular condition. So where I will have missed the sequence. Okay, I have to move on to the other state. Let me call the state as Q1, right? Yes, B is popped. Now, input symbol is C. What is it? Stack symbol is B. What should I do? I have to perform
Pop
pop
operation.
operation. Yes. So like that, all the B's will be popped off. Now my input symbol is C, my stack symbol is E. What should I do? I have to proceed with
Pop operation.
yes. E, I have to perform pop operation. Okay. So all will be popped off. Now my input symbol is epsilon, my stack symbol is Z naught. What should I
Z
do? I'll
naught.
be reaching the yes.
No
I'll be
operation.
reaching yes, no operation, I'll be reaching the
Final state.
finest hit, that is Q. Right. Try designing the piston automata for this A bar M, B bar M, C bar M, D bar M. Try designing the PDF for this. Okay. Also, try designing the PDF for this. A bar M. 2 minutes time. Okay. Please to make a note of this question. I'm going to stop sharing. Okay, we'll be back. Okay, please do make a note of this question. Okay. Have you all completed, ma'am?
Yes, ma'am.
This one. What about this one?
That's not a context-free language.
Yes. 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 Please make a note over here. So here, what is given over here? The number of A's and number of C's are equal. Number of B's and number of D's are equal. So you suppose I am pushing A and B inside the stack. What I will do, so in order to count the number of C's, I should be in a position to access A, right? So here you can see an example, B, C, C, D, okay? So here, yes, A, B, I'm pushing inside the stack. So here, if I want to count the number of C's, I cannot access A, only the topmost element I can access, right? So which is not possible. It is not a context-free grammar, context-free language. Okay, it is not a context-free language. So we cannot, it is not possible for us to design the push-down automata. Okay. Yes, ma'am. Please do try. So those who haven't yet completed, please do try this as well as try this one. We can see the solution in the next class. Okay. So please do complete these two. We can see the solution in the next class. I have already created a link for assignment. The questions are posted there. So please do complete the task. I have given the deadline till 31st. That is after the completion of your captive. Okay. So anyway, for TO's exam, you will be practicing questions, right? So you can practice it and you can submit it as assignment. That's it. Okay. Any queries here? Sorry, are clear with the topics discussed?
Yes, ma'am.
Yes. Okay, ma'am. That's it with the today's session. Uh, those who have queries, you can please stay back or else you can leave. I have downloaded that link. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.